Testing 1 2. Testing 1 2. Testing 1 2. Yeah, that goes before I turn down my test device. We'll be ready here shortly. Who we got? We got some beans in chat. Oh my word. It is a toaster. It is toaster. There I am. I'm like, where did I go? I thought I was here. Hello. Who do we got in here? We got some beans. Pyro and a set in a Pyrex. Hello, hello. Yes, that is my new getting started screen. It's something that I put together a little while ago. Very happy with the way it came out. Yeah, set position. There we go. Yeah, it's better. I'm facing forwards now. Haha, that's much better. Indeed. Yeah. So we're gonna continue with our 30 days lost in space. And then depending on what time it is, I don't know how much. Day 7 didn't look like it was a lot. I do have the BRB screen, yes. That one I've had for a little while, but I'm gonna be honest, I kind of don't really need it unless I need to take a break, which generally I don't do, but sometimes I might. It's fine. I'm not too worried about it. I just really wanted a starting screen. It feels more official. I mean, toasters can take breaks. Maybe. Let me see here. I said, I'm not. Do not put this in your queue, but I am 100% going to have that at some point. Live, laugh, toaster, bath. I don't know on what it might be. I honestly would probably make a pretty fun sticker, but that's going to be a thing at some point. I who was telling me that? I think Ash is the one that initially told me that. I thought it was absolutely amazing. It has not left me. How would you? I gotta stop myself right there, because if I ask him how he's gonna do that, he's gonna tell me in great detail. You're mad, Ladisette. Please don't burn yourself out. I'm not gonna ask questions because he's gonna answer them. I don't want answers. I'd rather it stay unanswered. We're gonna keep it that way. Haha. Moving on. Indeed, we are gonna do the thing. Oh wait, I don't have my thing up. I need the thing. I need the laptop. I need to be able to see it. No, now is not a good time to update things. Yeah, yes, Aset. I'm concerned, Aset. What's going on, little buddy? Yeah, I'm here. I'm here for it. I'm concerned. Should I be concerned, Aset? I feel like I should be. You know what? I'm gonna drink some of my tea. That's what I'm gonna do. That's what's gonna happen right now. No, you put it down. You put it down. My goodness. I don't even want to know what yes, the blueberry tea with raspberry honey. Folks, if you can get your hands on raspberry honey, this stuff is amazing. You pair that with blueberry tea, you're going to have a good time, okay? I ain't no food channel. We're here for technology. I'll tell you right now, you get your hands on it, you're going to have a good time. Stuff's amazing. I can't even imagine what your art queue must look like, Aset. My goodness gracious. I'm concerned for you. Oh my word. Real talk though, don't burn yourself out. Don't do that. I want you a happy artist. You're in a bargain. I don't know. We'll see. Okay, let me get myself rolling. I got that, and then I'm going to pause that. And then we're gonna go over to the other scene, which is here somewhere, which is that one. Excellent. All right, I got that, and then I'm gonna do that, and beauteous. Okay. All right. I said I do not have the capabilities to be able to make a 3D printed swooshy, okay? I'm gonna be real with you. If you could find me the STL for that, we could talk, okay? I do not possess the power to make that happen though by myself. Also, I hope you got a kick out of that cube that I made with the Discord. A bunch of fun beans while we were chatting. That was a good time. Okay, all right, I've got this up. Now, in all fairness, day 7 looks a lot like day 6. If you could find it, we'll talk. And I had thought I loaded the wrong module, but turns out day 7, we're expanding on the thought of the solar panels. So I have not reviewed this other than just the diagram quickly to see what I needed to get out of the little container, and turns out it's the same stuff. So on the workbench, I still have it hooked up. I didn't change anything. Now, granted, I did put it away and take it back out again, but beyond that, it's right there. So. No! Oh wait, I didn't say. Oh, I didn't agree to that. He's gonna. What emote is that? Oh my word! Wow, Miko goes fast. Holy cow! Roger. All right, that's concerning. No, you gotta promise me. You gotta promise me you're not gonna burn yourself out. Okay, not doing that. You are not doing this for a joke. Okay, you're not doing that. No. We won't have it. Okay. All right. Oh, let's let the computer talk. Let's get into it. I'm ready. I'm not sure I'm ready for what comes after stream, but I'm ready for this right now.
Rise and shine, Explorer. Our oxygen levels are steady, and our battery is replenishing nicely. That's cause for a small sigh of relief. Wouldn't you say? But let's not lose sight of the task at hand. We have another glorious day of repairs to conduct. Today, we're going to shift gears and delve into a bit of digital logic. We'll be learning about bits, data types, and why choosing the right one for your variables can make all the difference. Efficient memory usage is essential for our system to function optimally, especially on low memory devices like our Hero board. Moreover, we're going to expand the depths of our coding efforts. We'll work on a piece of code whose intention is to calculate our ship's battery percentage. Not only will this give us a clearer idea of our power situation, but it will also be a practical application of the concepts we're learning. Ready to get your hands dirty with some binary? Of course you are. Let's get to it. Well, aren't you lucky, Explorer? Today you get to enjoy a bit of a hardware holiday. How delightful for you. We're leaving the wires and boards be. They've had quite enough of your expertise for the time being.
Hey!
Before you start daydreaming about a leisurely day off, let me assure you, we're not on vacation. There is still much work to be done. While the hardware is blessedly out of harm's way for a day, we're going to fill the void with a thrilling, deep dive into the captivating world of coding. Yes, that's right. More mesmerizing mazes of bits, bytes, variables, and functions are waiting for your full attention.
Okay.
This isn't just about expanding your tiny knowledge base for the sake of it, you know. We're doing this so we can craft more refined, more efficient code. In layman's terms, smoother operations and quicker fixes lead us to a faster escape from this underwater blunder that we're in. So buckle up, Explorer. It's high time you familiarize yourself with the finer points of our Hero board's language. We've got some serious coding to do. Joy! It seems you're thirsty for knowledge, Explorer. We'll hold on to your seat. I'm about to drop some wisdom bombs on you. First, there's this delightful little thing called a bit, the smallest unit of data there is. It's binary, which in this case means it's either
She
0
better talk
or
about
1.
nibbles.
Its simplicity is quite adorable, isn't it? Combine 3 of these and boom, you have 8 unique integer numbers. Mathemagic. Next, let's graduate to the integer. It's a little bit chunkier, with a typical size of 16 bits. This gives you a marvelous range of about plus or minus 32,768. Not too shabby, wouldn't you agree? When it comes to integers, we're not bound by one path to stroll down. We've got 2, signed and unsigned. The signed integers take more of a straightforward path and have a bit that acts like a flag for whether the number is positive or negative. Unsigned integers, on the other hand, don't bother with this. As free spirits, they take the scenic route, living their life positively all the way, hence the bigger range of numbers. Now, take our photoresistor. It's a modest creature, outputting a value between 0 and 1023. It's just 10 bits worth of data because 2 to the power of 10 equals 1024. So, an integer is more than adequate to store it. But don't get too comfortable. Our battery capacity variable is set at a lofty 50,000, which outclasses the standard short integer maximum of 32,768. Thus, it needs the VIP treatment, which defines it as an unsigned integer. Next up, meet float. This one likes to live a bit on the edge, handling decimal numbers with precision. Imagine 123.4567. It has a precision of 7. Not bad, huh? Then there's double. It's a float that hit the gym and got buff. It's 64 bits of power capable of holding values up to a mind-boggling 10 to the power of 308. Veering off from variables, let's shine some light on void. It's what we use when we're defining functions that don't give anything back. We'll dive deeper into creating our own functions soon enough. So there you have it, a crash course in basic digital logic. Its overwhelming nature is similar to drinking from a fire hose. I know, but fret not. We'll be practicing these concepts soon enough. Shall we push on, then? Today's mission involves writing additional logic in order to print the battery percentage to our handy serial monitor that we discussed yesterday. Of course, we don't want to spend time rewriting the print statements all over the place in our code. Instead, we can create a new function. We can start with the word void. This is what the function will be returning. As you may have guessed, void means that it will return nothing. This also means that we don't need a return statement.
You're okay, Seth. We'll take it a step at a time.
I recommend you name it something relative, such as print battery percentage. The parentheses can be empty since we have no parameters we need to pass into the function. Finally, everything inside the brackets is what will execute when you call the function. When the second closing bracket is reached, it will return to where it was called from in the code. If my assumption is correct, it is likely setup or loop. In the end, your newly created function might look something like this. For the line by line, let's jump to the information cached on your computer. I've also added this to your mission resources for future reference. I'll be waiting patiently for your return.
Hello and welcome back to day 7 of the code.
Hello and goodbye. Do 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 do. No sad faces. I'm gonna explain what we're doing. I just like letting that little bit play because that gives at least a little bit of preface before I start talking. It kind of gives me no sad. No, it's such a sad emote. I don't know. Does it? All right, you tell me. Does this rival Cashew's Kitty? Because I arguably think that's more sad than my little sad toaster. But sad toaster is really sad. So I don't know. It's you tell me. Because no one wants to see a sad toaster. He's so sad. You can't do it. We're not gonna do it. Oh, it's fine. Okay. So as the fancy lady said, it's not illegal levels of sad. You know, that's completely fair. I'll accept that. Oh my goodness. No, not the maple sad face. Ah. See, she gets me because she has the rain in that emote. That's just extra sad. Oh. No. No sad. We don't want sad. Why do we have so many artists that can do such sad faces? My goodness. Seriously though. No, I said I do not need that level of power. Thank you. I will say no, because I'll probably short out. We don't want a sad toaster that's also shorted out. No, we're good. We're good. I promise. All right. Good news. I did leave the code available to us. And it's cranking away here. I don't want to clear this just yet because we are working with the same circuit, but we're going to do different stuff with it. So I'm going to scroll back up here. We are going to start a new project. I am going to open up a new instance and open up the serial monitor again. I think it'll hold it. No, I don't want lightning, electricity lines. No lightning and no wire. Yeah, here. Oh my word. Don't short out the toaster. I do that all by myself, thank you. All right, where am I at here? Okay, so this is from last week. but we are using the same circuits. So I do just want to point out what we had from last week and what it's up to, and then we're going to change some stuff. Right? Yeah, instance. Yeah, or if you hear the word soup. If you don't think of the same individual I do when you hear that word, yeah, I think I've made my point. Telling you. There it is. I knew that. See, it's just it's a call out. It is, but it is like, oh, bugger. All right. I'm getting sidetracked again. Yes. Okay. I'm not going to run through all this like in exceptional detail or anything. I just want to point out that we are using the same code or the same hardware with different code. We're going to leave it the same, right? So what we did last time is we used the photoresistor that's in the board, stored the darkest and lightest value to give us a range, and then used the map function to give us a sliding scale that would take one number and map it to the other, right? Let me put our music back on. There we go. Okay. And then we would just blink the LED that's on the board, the built-in LED, which is why LED underscore built-in. We didn't declare it up here. Other than its mode, we did declare that. I lied. In the void setup. So to cover in a little bit of better detail of what she meant by void, void and the stuff inside of the curly braces simply means that it's going to just run the code, but it's not going to hand anything back to the script as a whole, right? Because this entire code block we have here is the whole script, right? So when this function runs, now this is the setup function, this only runs once, right? But our loop is what's down here, right? All the way down to the bottom, right? So all this right here is our loop, right? The fact that it's a void function, we don't put anything in. Actually, we could put stuff in, but in our case, we're not. Kind of close. It's pushing a button and the machine doesn't do anything outside of it. So if I gave you a black box with a red button in it and you clicked it, it's doing something, but you don't see what it's doing. There's no outward output. Nothing came back to the code further down. So if I had a function that would return the status of a light, on or off, well then when you run the code, regardless of what it's doing, at the end either the light will be on or it'll be off, right? That's a function that does return something, but voids don't return anything. They can accept inputs, but just nothing comes out the other end. If you have a function that returns something, then at the bottom of the block, right, so our block starts up here, right at that curly brace, and it ends here on line 45, right above my ears. There would be a return line, and then you would return a variable worth of stuff, and then you just mosey on through. The nice thing about functions is that you can call them multiple times. In our particular loop we have here, this loop function, this just loops forever, right? But functions don't have to loop forever, like the setup function. This only runs once. The loop function runs until you lose power or you hit the reset button, right? So with that, we're going to dig into what we have here today. So we're going to do a new sketch. And then we're going to save it. Okay, I can see the name up there in the top. So we got day7. Sketch. not quite that kind of sketch set. I'll keep those kind of sketches in your very capable hands. Okay, so I also want to turn on our ability. No, sad, get out of here. You're fine. You're the one who sketches in artness and amazingness. I'm the one who does the beeping and booping here. Now, here's something that's gonna blow your mind a little bit. I have the sketch open, and behind my ears, we're still seeing the code running that we programmed from day 6. As I had mentioned previously, I had yet to actually reset the board. So the board that's currently cruising here on the bench is still blinking, right? And if I hit that with a flashlight, it's gonna blink faster. And then it'll slow down, right? And the light values, right? If I hit that again with the flashlight, they go high. And then they come back down again. The code that we pushed to the board is still working. We haven't erased it yet. So we're gonna still see this code until I send the next sketch. The serial monitor is just simply that window that shows us what values the code is returning. So I'm gonna reset it by just validating and sending the empty sketch. It's done uploading, and our serial monitor has stopped. There's no new numbers appearing here. If we take a look at the bench, the LED is no longer blinking. It's no longer doing anything. And if I hit that with the flashlight again, nothing has changed. It didn't speed up, didn't slow down. The values didn't change on the screen because the code that we previously used from last week is no longer in the board. So do keep in mind, if you are working on new code, that your board is still holding on to what you used from the previous iteration unless you reset it. To make this make a little bit more sense in our context, I've reset the board because what we're doing is going to be new code. So we don't need to see this old information. Actually, I don't know if I can clear the serial monitor. Probably not. I don't see an option to. Ooh, clear output. That's better. Good. Okay. So now anything we see in the serial monitor will be new data. As of right now, there's nothing going on, so there's no information in the window. So the first thing we're going to do is swing back over to our exercise, and we're going to pick this apart and bring things over one at a time. I'm sure a set you would enjoy coding. There's a fair amount of fun things you can do in the coding space. Okay, first things first, we want to be able to use the classes that are built into the Arduino board. So we have to include the code that does that. So above our setup, we're going to include the Arduino class that then allows us, excuse me, the Arduino package that includes all the classes, functions, all that good stuff that allows us to play with the board. Even though the Arduino IDE is Arduino branded, if you don't include the class, the code that makes the Arduino work won't function. That's just because it's a code builder, you know? That's all it does. So if you don't tell it you want to be able to use the stuff that you very much want to use, it's not going to work. Luigi board. No, we're not conjuring demons in my stream. No, thank you. Oh, that game. That's such a fun game. Run for the hills. Okay. Now that we have included the code that allows us to do other stuff, we're going to then declare our variables. Now, our constant, the type of the variable is a byte, as she had mentioned. The byte is the smallest unit that a variable could be. And as we know, a pin is either going to be on or off. Or wait, no, I lie. The name of this it's storing is a byte. And the values could be anywhere between 0 and 1023 from that. And the byte permits us to... Our values that could come back fit within the range that the variable of a byte can hold. Without that, it would cause an overflow or a memory leak. Because if you get more data coming into a variable than it can handle, it causes the code to fail and you get unexpected results. And that could mean many things, which is why I just simply say unexpected results, because it doesn't do what you want it to. And that is for our photoresistor pin, right? So that's going to read the leg of our stuff on a 0, which is where we are currently wired. The byte of 87. No, this is not FNAF. Nice try, though. Okay, we have our pin, and then the next thing we want to declare is our battery capacity. Now, she didn't specifically say this, but yeah, or a nibble. That's right, she didn't mention the nibble. A nibble is still a multiple bytes. It's 4 bytes to a, or was it 2 or 4? I think it's 4 bytes to a nibble, and then 2 nibbles and a, no, 4 bits to a nibble, and then 2 nibbles to a byte. That's what it is. She had mentioned that because I guess it doesn't apply in this space. And then there's like 2 million nibbles to a gigabyte or something. I don't remember the exact number. We did it once. It was big. It was a very large number. Very sizable. There's a lot of nibbling involved to get to a gig. And forget about a terabyte, man. You'll be nibbling forever. Let's see here. Unsigned integer. Our battery is 50,000 in capacity. In my mind, this is in milliamp hour. Oh, MAH. Let's try that again. Petabyte. Long time. Long time. She doesn't specifically say that, but I'm thinking that the battery on our little ship is likely a power bank. That's what it sounds like to me. So I'm declaring it's in milliamp hours. This is just simply a comment, and if you do have something that describes your variable better to you, then add that. In my case, I think of this as in milliamp hours, and since I wasn't told it was something otherwise, this is what we're using. So we're going to declare that, and then we have to set up to get started. So our setup is code that is only run once. And we are going to declare the mode of our pin resistor that we did declare outside of the setup function. Now, since this code is going to run in an endless loop, this stuff that's above the setup function does also only run once, even though it's outside of void setup. I don't know why we're putting it outside of void setup because I don't have that context. But just know that if it's outside the loop, it's not running until it loses power or starts over again with the reset button. Oh yeah, 10,024 gig and a terabyte. Same thing with RAM. 4 gig of RAM is 40,048. 1024 is the increment. It's a funky thing. So it's not false advertising. It's just they're including. Okay, so hard drives and marketing. I have my own beef with those. You are getting what you pay for, and the reason for that is that the marketed value is correct when you purchase, say, a 5 terabyte or a terabyte hard drive. The issue is that there needs to be the record table, which is on there, that records where you the journal. I think it's called the journal. Actually, is what records where your things are stored on the disk, and that takes up space. And regardless of how you format it, there's always going to be a journal table. So yes, it's not false advertising, but it kind of is. But it isn't. Infinite swishy loop. I saw that emote. My goodness, or that loop. That was ridiculous. All right, sidetracked to the maximum. Our photo resistor is an in pin, which is very nice, because we're reading the levels on that pin. And then we are connecting to the serial monitor again. And this is the code that begins our connection with it, which we only need to connect to it once in the code, and that just keeps reusing it and keeps redrawing to it. But the connection is established and stays there. Not too crazy. Okay. What's the next item we have on our to-do list here? Use global here. Excuse me. Using global here because this variable is accessed both within the loop of our custom function, and later in the lesson we will show how to avoid globals. Interesting. Okay, so I am interested as to why they... Alright, so they probably put it out here as an example, but I can tell you right now, unless you require a global variable, don't use it. There's better ways to handle information between loops. So since this variable is declared outside of the void loop, that means that if I had another function, the value of that variable is accessible to all the other loops that are available. Or excuse me, all the other functions, including the loop, right? So if there was a thing inside the loop to break out of it, which I'm sure we're probably going to reach that point sooner or later, you would then be able to take that value and move along with it. If you have a variable that is declared and only used inside of a loop or inside of a function, whether it's a loop function or a function that may return something, it only is accessible within the function. Once the function is ended, you can't call that variable outside of the block of code. So inside of the loop here, right, there's this curly brace up here, and then there's the curly brace down here, right? If I try to call the variable inside of this block of code down here below it, it won't work. It will say something along the lines that it's not declared, or that it's inaccessible. Because it is. So there is this thing called variable scope. Depending on where you make your variable dictates when it's accessible. And we'll see more of that, I'm sure, since they're actually picking on it right now. So let's see here. So I find that interesting that we're declaring this out here, but that's okay. All right, so it makes perfect sense that for the first instance of our unsigned integer, that the battery level is at 0, right? If we don't declare the value of the variable is 0, that's different than the variable being equal to nothing, right? Because 0 is a value. Null is the idea of there being nothing in a variable. It's empty, but it's empty in a different kind of way. There's nothing currently stored in it, right? There's different kinds of code that you'll bump into in the world, and there's different ways that things could be declared as being empty. I'm gonna put this in chat. If I did double quotes like that, that's an empty string variable. If I do just a 0, that would be the beginning of a integer, right? To us, that means nothing because it's 0. There's nothing, there's no quantitative thing to 0, but there's also the idea of null, right? Null is if you don't put anything into the variable, you've just simply declared it, but you haven't stored it, stored anything in it. Not quite. We're working with different types of variables. the battery level maximum is 50,000, as we have mentioned up here under our battery capacity, right? So that's not binary, that is a unsigned integer. So that is a different type of variable. Now, don't get me wrong, the number that makes up what we're seeing here as an integer to us, right? We count in integers, right? There's 1, 2, 3, 4, 5, is stored in binary. So there's multiple ones and zeros that we don't see that stores what our number actually is, but that happens in the background where we don't see it. Once we compile the code, the board manages that at the storage level. We won't see it. Okay, so the next thing we're going to do is display the battery information on the serial monitor, which is the bottom of our little code box, right? If the battery level is less than the battery's capacity, that means it's not fully charged. It's going to start from the go at 0, right? So 0 is less than 50,000, right? Which means that out of the gate, we will always fall into this if statement. If at any point the battery level is greater than the battery capacity, then we've reached the point. If it's just not less than, let me say it that way. So when we reach the point that the battery level is just simply not less than the capacity, so that means that the battery level is at 50,000, or it's more than that. Say it's 60,000, right? That doesn't really make a lot of sense in this context, but by the way the code reads, as long as the battery is at 50,000, that is not less than 50,000, right? Because there's no or equal to, right? It's just simply less than here. That's what this operator means, the little left caret that I'm highlighting with my cursor. We will fall into this function. So if the board first powers on, we're always going to fall into here, because up here we could see that the battery level is right there, a 0. Now the battery capacity we declared above it is right there, 50,000. 50,000 is always more than 0 forever, right? So when the code first starts, we're always going to land in here, right? If statements don't run every time. If statements only run if the function is true, right? Now there are certain if statements that have multiple conditions, which is where and or statements come in, but I'm not going to get into that right now. Just know that an if statement will not run if what is inside of these parentheses needs to be true. So this is the condition that we check, and then anything that's inside of the curly braces that make up that function, which is between here to here, right? That's the if statement. I know your brain hurts. I know this stuff is kind of mind melting, but the getting to see it in action is, some of the best parts. Think of it this way, right? We have the battery capacity and the battery, right? So say that you have 0 cookies, right? And if you start with 0 cookies and the jar can hold 50,000 cookies, right? Well, once you have enough cookies in your hands, right? Once you've reached 50,000 cookies, then this if statement won't run again and the contents inside of it. So yeah, I'm gonna pull this and bring it over. Okay, so once this is true, which it will be on first run always, we then go into the function, right? So we see here that the battery level is plus equals analog read photoresistor pin. Read the light level and add it to the battery level. So we're going to actually read the level of light from the photoresistor. Remember from before that when we hit light on our photoresistor, it can return up to 1023, right? Somewhere between 0 and 1023, right? So we're going to read that from the component and we're going to store that into the battery level variable, right? So the idea here is that the sunlight or my flashlight that's going to hit the little sensor would be like our solar panel. That's the whole idea of the exercise. With that, we have a plus equals, not just a normal equals here. So a plus equals means that if there's something already in this variable to our left, it is going to add on top of it what's already in there. If I didn't have the plus symbol and this was just simply an equal symbol, the battery level would be equal to whatever we read from the photoresistor, and it would never get any bigger. The next time that the code would run again, we would just be equal to what was ever in from the photoresistor. It just reads the value and just restores it. So the plus symbol is very important here. Without that, this code won't work the way we want it to. And then there's this thing called a nested if statement. So we have another condition that we check that lives inside of the first one, right? This second if statement that we have here will never run if we don't fall into this first if statement, because it's inside of it, also known as a nested if statement. So inside no runny, if outside don't runny, right? Because if you had two doors in your house, right, and this first if statement is your front door, and this second if statement is your closet, you can't open the closet door without first going through your front door. Same logic applies here, okay? Same kind of thing. So now that we've read it and we've added our light to our battery level, we then make another check. If the battery level is greater than the battery capacity, this would make the charge over 100%, right? So that's what we're checking for here. If that is the case, we are then actually going to modify the battery level and set it equal to the battery capacity. So that prevents our display from going over 100%. Now there's a reason for that. In this example, we are reading whatever comes across the photoresistor pin, right? So say that we ended up with a 900, right? And we kept reading 100s, right? We read a value of 900, a really bright flashlight, and we read that. I was gonna say about 20 times, but that only works out to about 18K. So let me take 50,000 and divide that by 900. Right, that would then mean that it would have to read that level almost 56 times, right? Now, 55.5, right, is a oddball number. So say that we read it a total of 56 times, right, at 900. So if I take 900 times 56, that means we've put 50,400 milliamps into the battery, right? That's not a real value, right? Because it's larger than what our battery can hold. In the example, this simply just prevents the example from making no sense, right? If we were charging an actual battery, right, we would check the amperage level of the battery to see if that was done charging, which means that we would never get a value that's larger than what the battery can hold, because that doesn't make any sense. But in our example here that we're working off of, we don't have a true solar panel. We just have a sensor that could read light, and we're just storing whatever comes back. And this loop is going to run multiple times to simulate the idea of the battery charging. This little block of code down here just prevents us from seeing a value over 100. And that's perfectly fine. But just know that that's there because in this use case, in what we're actually doing, has the potential to go over 100. And that's not because the battery would be overcharged, but by the way that we're getting the value that we are then using. Okay. So now that we've got that, we are then going to see some stuff here. What do we got here? Previously, we've only used the functions included in the Arduino C++ language. Here we demonstrate how to use our own functions. This keeps our main code cleaner and easier to understand. All you need to know here is that this new function prints the current charge level on the serial monitor. Okay, so I am going to just pull this over so we can see it. I need to be careful here to make sure I pull what I actually need. That's down there. Now, what is this curly brace to? That is there. That is within our loop, so I don't want to copy that. So I want to copy these two things, and then I'm going to explain a little bit about what we got going on here and why things are being placed where they are. So this is where things can get a tiny bit confusing. But I promised you I will explain what we're up to. And I'm going to verify the code first to make sure I didn't make a boo-boo. And I did. Ah, all right, that's why. So the thing I why I wanted to bring this over was to show. So this is something that is unbelievably useful when it comes to hunting down missing curly braces, which is what these things are. You can actually collapse the code in the viewer, and if you're missing a brace, the code won't be collapsible. You'll actually get red like I got there on the bottom. Okay, so first thing I want to show you here, this is the first time we're doing this, right? Now, everything else we've done has always been within the loop, right? And the loop would run forever, right? We have code for the first time that's not in the loop, right? The loop ends right here on line 40. And I can collapse that and I can prove that. I've collapsed it, right? So we can, the code's still there, we just can't see it. It's a visual collapse, right? Hacker toaster, exactly. But on line 42, we've got this function that says print battery charge level. This is C++. What's happening here, and the reason why you would write functions, is you can call them. Right? So you'll be fine. So the thing is, C++ is an object-oriented programming language, right? Let me explain what that means in normal people terms, right? It's compartmentalized, right? So the idea of a function is that you call the code and you can call it multiple times. And that code will only do the one thing you told it to do, right? Let me give an example that's not coding related, right? Say that you wrote down some instructions, right? About how to prepare a bowl of ice cream, right? On the instructions, at the top, it says how to make ice cream, right? Or prepare ice cream, right? That's going to be the name of the instructions. Prepare ice cream, right? And inside of our prepare ice cream, we go into the function, right? So Chords coil. Python sneak? Oh, no, it's not Python. Python is a tab oriented. You're not dumb. Get out of here. We're talking about some fairly complex topics, okay? You're fine. You're fine. We're working through it, all right? So we have... No, it's neither of your jobs. No one here is dumb, okay? We're talking about stuff, right? And we're doing the learning thing, or at least we're attempting to. If anything, if you're listening to me, I hope you're at least mildly entertained, or you find something useful out of this talk. it is what it is, okay? I don't expect anybody to be running off to the terminal land to go clacking on the keyboard, but it's a good time. The swishy is real. I love that. But we have our instructions on making a bowl of ice cream, right? So make ice cream, right? What's the first thing you have there, right? You grab the ice cream scooper from the drawer, right? And then you grab the ice cream from the freezer. After that, you bring a bowl from the cabinet. You then take your scooper that you declared earlier. You scoop some ice cream out, right? That gives you a quantitatable amount of ice cream, right? A scoop or 2 scoops, right? And your function has the opportunity to take input to ask the user if they want 1 scoop of ice cream or 2 scoops of ice cream, right? 1 or 2. And with that, that's a function that can return, right? We obviously don't want a void function, because if I call a function that calls make me ice cream, make me a bowl of ice cream, well, I want the ice cream. I don't want it to prepare the ice cream, scoop it out, put it in the bowl, and then give it back to me by not giving it to me, right? That void function wouldn't give it back, right? There's no return, right? But a function that returns a value is what we have here, right? The print battery charge level function. What it does is it's called inside of the loop by its name, right? Just like I'm gonna call a set an amazing artist because he is, and that's his name. That is his function name. That's how you get his attention, right? I am TechHead41. You use that. That is my name. That is how you get my attention, right? Same thing with a function declaration to call it, to use it. So let me expand out our void loop here. And you can see here, after we've gotten the value of our battery, no, it's set. You're gonna poke fun at me, I'm gonna poke fun back. We have right here, print battery level, battery charge level in an empty set of braces here. Yes. Because we're not providing anything to the function. So this simply calls it, and then it jumps over this delay. It doesn't run that. It comes down here, runs this block of code, and then when it's finished the function, right? This is a void function. It returns nothing, right? It reaches the bottom of here. It goes back up here, hits the delay, and now we're back in the loop. That's the bottom of the loop. We're still within the loop because we came back up to it, and that scoots us back to the top of the void loop, puts us back up here, and we run through it again, right? So as I embrace just fine, artists, okay? Captain Aset, you are the swishy operator, okay? You draw the swishies, the big swishies. Oh my goodness, what is this conversation? Oh, we're fine, you're fine, okay? It's good time. 110%. Why am I looking in the corner? Thank you. Okay, so back to the ice cream example, right? Because I'm not quite done with that yet. If this function was not a void function and it returned something, right? At the bottom of the function, we would see the word return, right? And then it would return our bowl of ice cream, right? And I could keep calling that function to make the ice cream as many times as I wanted, and each time it runs, it gets the scooper from the drawer, it gets the ice cream out of the freezer, it then gets me maybe 1 or 2 scoops, or maybe that's random, maybe it just randomly grabs 1 or 2 scoops of ice cream, puts it in the bowl, and then it returns back to the main function, right? Or excuse me, the main loop, 1 or 2 scoops of ice cream, right? In this particular case, we are not required to get anything back, right? So that's why the function is void. It returns nothing. yes, the swishy will destroy you. It's not my fault you make amazing art, okay? You're just that amazing. That's how this works. There's a whole community will tell you this, myself included. Okay, and then we delay by 100 milliseconds, right? So 100 milliseconds is a reasonable amount of milliseconds. Hair. You're not going anywhere. Nice try, though. Okay, so I've talked a whole lot about this, what this function, how this function is called. I did not go into what it actually does. So let's look at that next. So our loop runs, right? We connect to the serial connection in void setup. We then run through the if statement. As long as the battery is less than the full charge, we then we read the light value from the resistor. And then as long as it's as long as the battery level is less than the capacity, then this if statement's ignored. If it ends up being more than, like I said, this is just an adjustment, it makes it equal to it, and then it's truly fully charged. So this all by itself prevents us from accidentally going over 100, right? Now, just because I can, I'm going to omit that code so we could actually see what happens when that's not there, right? They provided that for us, but I'm going to take it out. But not before I run it the first time the way they want it. Okay, so we call on the function to print to the terminal our current level of charge, right? So we've read the light value from the photoresistor, right? We then spit it out to the terminal, delay by 100 seconds, and then go again. And then we keep doing that until the battery shows 100% charge, right? So to get that, we need to do a little bit of math, right? Everybody's favorite thing to hate, math. If we take, if the battery is less than the full capacity, we know it's not fully charged. So then we'll then go into the if statement here, which is this first chunk of code, right? There's this else thing on the bottom, which we'll get to, but just know the if statement ends right here. It's just this portion up here. We write to the screen, which is this serial print, the battery level, which this type of variable is a double, and we're declaring that inside of this pair of parentheses, right? Now we're doing some math to these variables, which is why we're seeing some extra parentheses here. We are doing some math in the order of operations. So when we look at this, we take the battery level, which we get from the photoresistor. We then divide it by the battery capacity. Now, I don't want you to get confused here, because I'm looking at this and this would be confusing if you didn't know this. The battery capacity is a type of double. Double is the type of variable that's holding the number, because as we saw up here, the battery capacity is 50,000 and it's an unsigned number, right? So that allows it to hold the number 50,000, right? Now in the context of down here, the battery capacity is a double. We are not doubling or multiplying anything by saying this. We're just simply saying that this variable is of the type of a double to hold the number that we have. It just simply declares the size of the container. That's it. We then take that battery level, divide it by the capacity, and multiply it by 100. That then gives you the percentage of the charge. Now, for me to pull up that as the idea of an example, right, so that we can actually see what that looks like. Say that the battery capacity had 10,000 milliamp in it. If we divide that by the full capacity of the battery, it's 50,000. That gives us 0.2, right? Now that's the decimal version of the capacity, but we want to show it in percentage. So if we multiply that by 100, that's 20% of the battery. That's why we're doing it the way that we're doing it, by multiplying it by 100, to move the decimal point over, to convert it to a percentage. Now, we can see here that we're going to display the value of the battery. And then we can see here that there's this else statement. If this if statement is not true, that means this code below is an else statement, which means if the if isn't true, you're going to run this block of code regardless, every single time. Only if the if statement isn't true. If the if statement's true, it ignores this else. So it's if this, else do this, right? If I wanted this block of code to still be conditional, then it would be an if else statement, or just another if behind it. Now, if they're related to each other, usually it would be an if else, right? Because you can have multiple if else statements behind each other. What does that mean in context of anybody who has a brain, right? Say you have a colored shirt on, right? If the colored shirt is white, right? In the first if statement says if blue. All right, we're going to ignore that. Go to the next statement. If the next block of code says if else, then we'll compare the next shirt color. I'm wearing white. My lab coat is white. I'm wearing that right now. If that next color is looking for orange, then it's going to go to the next if else statement. It's going to keep going through them all until either it finds one that matches or we reach the bottom. If you have an if statement in multiple back-to-back, you always want the last statement to be an else. If you have if else and the last one is an if else, that's not good form, and that can cause you trouble because you can miss a case that you didn't anticipate. An else statement is a catch-all. So if none of the if statements above it are true, that last one in the bottom, that else, captures it. That ends up being the last key you fall into, which means that as long as the battery percentage is not smaller than the capacity, then that means we are fully charged. So we don't need to check anything. We can just simply tell the user that the battery is fully charged, which is glorious. That's what we want. So I've talked a whole bunch. So let me compile the code now. We're going to run it, and then I'm going to do some stuff to it because that's fun. Okay, so as it stands right now, I've compiled it and I got no errors. So I verified the code, right? Now I'm going to actually send it to the board, and then we're going to start seeing some output in our serial monitor down here. As it stands right now, nothing's going to happen on the board itself because we're just reusing the same stuff as it sees fit. And currently there's nothing to do with the current LEDs that are on the board. This code does nothing right now with the lights on it. Okay. So without further ado, I'm going to send the code. And away we go. Gonna resize this so you can actually see the numbers. So right now it's reading the room, right? And my ambient light in this room isn't super bright. So we're charging, right? And you can see that there as the numbers are incrementing, but I'm gonna hit it with my flashlight. We're gonna go fast. Let's go. Boom! Just like that, we've hit full capacity. Now that was a case of gotta go fast, right? Speedy. Very incredibly speedy. If I send the code again to recompile it, that will reset it. And then we'll start over again. Now, if I cover this, you're going to notice something. The numbers are still going as fast, but we're not incrementing barely at all, right? Because I'm blocking the light from the photoresistor. So we're still climbing, but it's taking a lot longer because it can no longer see the ambient light, which makes perfect sense. If this was actually a solar panel, that makes sense. Less light means less charge, takes longer to do the thing, right? And if I uncover that, it's going to see the ambient room light, and it's going to pick back up in speed again. And given enough time, that's going to work its way back up to 100%. And we'll just give it a moment. I have to say that this is probably the fastest charging battery I've ever would have seen if it was actually charging the battery. Can we get cell phones that charge that fast? Please? That'd be kind of awesome. There we go, and away we go. We are now fully charged. I like it. Now, the way that the code is compiled, this will never stop. It's just going to say fully charged because it's now finally reached the end. There is a bit of a delay with the 100 milliseconds of delay, but it's just going to keep going forever. And there's nothing that can happen at this point, by the way the code's written, that would prevent that from saying anything other than fully charged. Because the value of the serial monitor has reached its maximum capacity. So there's nothing here that's going to not show the percentage anymore because it's fallen into that use case, right? So now that it's fully charged, right? What that's looking like if we look at the code, right? In our loop, the battery's capacity is now equal to the capacity, or the battery level is now equal to battery capacity, right? Which means if the battery level is greater than the capacity, which it won't be because it's looped multiple times, that doesn't run. We then go into the battery level charge function. Now, if we didn't put this code, if we put this code that we have that's down here, up here in the loop, we totally could have did that. It totally would have been valid. But by declaring it as its own function, that makes the loop smaller and easier to manage. Because we just want to know what the battery percentage is. By calling this function that we have up here, we're calling this block of code, but it can be further down out of the way. So if we have to troubleshoot the thing that returns our level of charge, we're only troubleshooting this small block of code. If we just put all of the code for everything we're doing into the loop, it's going to get really big, right? And as we do more complex things in the 30 Days in Space courses, this would become unmanageable because we're going to have more code. This is going to get bigger as time goes on, and we don't want to get lost in the mix of everything, right? So that is part of the reason why we have this function. Not only does that introduce us into taking code and putting it in a little box for ourselves to be able to call and put back when we're done with it, it makes things easier to read. Okay. Now there's something that's irking me about this particular example that I don't like, and we're going to fix it. I don't like the fact that there's no light. Every battery in the existence of forever has a light. What battery do you know of that doesn't come to a full charge, that doesn't light something up? I am actually surprised that we don't include toggling the onboard LED at least to indicate that the battery's charged. I don't know why that's not a part of this example. Maybe because of the fact that the code is a little bit more complex and they didn't want to fry anybody's brain, but I don't like that. I don't like that. So we're not going to do that. We're going to modify the code because I want a light that comes on. Why, thank you, Aset. You are delightful. We're going rogue. We're going rogue. I want a light. It was cheesy. Is it like cheesy dip? Cheesy dip's amazing. That sounds like a good time. We should do that. Anybody want soft tacos? Add the cheesiness to it. Sounds like a good time. I'm making myself hungry. I should stop. No food topics. Listen, I can talk about food too. I just not to the extent that everybody else can. I'll just get hungry and I don't want to do that. Okay, so since I want to take some thought from previous example, I'm going to open it. I gotta find it, hang on. That's the day we're on. Okay. Now, I'm just gonna hide the monitor on this one because that's unrelated. I gotta find it first. There we go. Okay. Now, I opened back up day 6 because I want to pull some code out of this and use it in our day 7 activity we have here right now. So, we're still getting our fully charged capacity. And the serial monitor I turned off in day 6 because it's unrelated, just so we don't get confused. If I switch to the bench right now, we are seeing a blinking LED, which I have to actually check. Let's see which one that one is. That is our receive LED that's blinking really fast right now, right? But the onboard LED is this one right here that we can change the programming on. So what I'm going to do, because that's the power, that's data moving back and forth. There's transmit and receive. That's the RX light for receive. Transmit's not lit up right now. And the L onboard LED is currently not in use with our code as it is right now. We're going to change that fact. So the LED that is the farthest from the edge, we're going to use. And what we're going to do is we're going to make it so that when the battery hits 100% capacity, we're going to have that turn on. Because what's a battery charger without some kind of visual indication? Sure, I could look in the terminal and see that it is fully charged, but I also would like to see something in the real world change. Which is what we're going to do. We're going to do it! Yeah! We are doing it. Go for the sushi. Oh, goodness. Now you say sushi, but I read swishy. I'm sure it's fine. Will it be though? Okay, so I want to control the onboard LED. So I need to do some stuff here before I can do that. So from our previous example, I need to set up the pin mode for the built-in LED and put it in the void setup that we have over here. And I'm going to add a comment. We will light up this LED when we have hit 100%. So we're going to declare its mode right there, and just a note here of what we're using it for, just so it's easier on ourselves. And since it's built in, I don't have anything else I need to do to declare it, because it's LED built in. Now, we know for a fact that we don't want it lit up when we start the code, so we need to tell it that we want it off, because right now there's no code that's telling that LED to do anything. And as we see right now, the LED is on, which is not the state we wanted, and we want it off until it reaches 100% battery capacity. So we are going to put in the top of our loop, or excuse me, the top of our void setup, that we want it off. So we're declaring its mode and we're turning it off. Now, our void loop we can ignore, because down here, when we reach the point that we are fully charged, that is the status that we have reached 100%. And at that point, we want the LED to come on, right? So what we're going to do is we're going to put the statement that turns the LED on. And we're going to put that right there. I'm going to verify my code to make sure I didn't forget anything. And we are valid. So I'm going to send that code to the board now. And we're starting back over. Now, if we take a look at the bench camera right now, that LED is not on. The top LED is the power light. The one that's blinking right now is the transmit LED. And then I want you to keep a sharp eye on the LED on the bottom, because once we reach full charge, it's going to turn on. And I'm going to help it along by hitting it with a flashlight. I'm going to pick this up so you guys can see it. I'm going to hit our photo resistor with a little more light. And there you go. Just as we've reached 100% capacity, the LED right there came on. So now, not only do we see that there is a fully charged status in the terminal that we can see, we also change the status of a physical piece of equipment in the real world, right? Now, we're not new to the idea of turning LEDs on and off using this board, right? Because we've done it before in previous examples using the toggle switch, right? Physically toggling that LED on and off when we want to turn it on or off, right? That was the cabin lights example that we ran through before in previous weeks. But this is one of those times that we're using automation to determine when the LED should turn on, right? Now, once it's reached that if statement, or excuse me, the else statement, right? The else that happens after that, we can have that LED do anything, right? Once we've reached the point that it's fully charged and we're in here, we know that to be true. We can make it blink. We can make it, I was gonna say flash, but that's blink, right? At different intervals, different speeds, right? Something to indicate that the battery's done charging, right? Because we could do more with this, right? Instead of having the LED be off the entire time, how about we have that LED blink during the time that it is charging, and then go solid when it's done thinking, right? Almost everything that you could charge in today's world blinks when it's charging, and then it goes solid when it's done. Sometimes the LEDs change colors. There are multicolored LEDs in this kit, or at least one. I'm very looking forward to us playing with that, because I don't know how to wire that. But when we get to that, I can assure you we're going to play with multiple colors. Yeah, let's do that. We can totally add that in here. So we can see here right now that let me think about how I want to add this in here. Rainbow time, exactly. So we'll say that we'll turn this on, and then we'll delay for 500 seconds in the code, and then turn it back off again. So that's going to cause this to kind of slowly blink as we cycle through. Now that's going to slow down the code. And the reason being is that this delay of 500 milliseconds is in the function itself, right? So that's okay that it's going to slow our code down, but that's also, I want you to keep in mind, generally you don't add delays to your code, because if you artificially delay the code, the longer it takes to compile. But in the case of us looking at an LED, we need to add a delay or we won't actually see the change. But know that when you're writing your own code, delays normally aren't required, because usually you write your code to interact with something else that's happened. Or you check to see if something's happened, and then you just keep rolling through it. So I am going to compile this. I'm going to send it to print. The terminal is going to reset. And now we can see behind my fluffy ears that we're not moving as fast. These values are taking longer. Now, if I go back to the bench camera, check it out. We're blinking. Now, the rate at which this blinks is not going to change because it's hard-coded at 500 milliseconds, right? But we're slowly going to blink until we reach 100%. So I'm going to hit this with the flashlight. And I'm going to give it some good hits here. So we're at 30%, 32%, 40, 50. Oh, we're almost there. 70, 80, 90, almost got it, 100%. Now, something happened that you didn't see. I'm going to reset the code to show you what you missed. So, LED's fully lit up now, right? And the terminal is back to full speed again. It's moving faster like it did before, right? So let me go back over to here, right? We're now running at the same speed. We're going super fast again, right? Because I put the delay for the LED inside of this if statement. So the battery is now at 100% capacity. So this delay of 500 milliseconds no longer applies. It's just going straight to the else statement, turning the LED on each time. Now there's nothing in here to indicate for it to shut back off. So it just keeps setting that state to being turned on, which is fine. But the code is now going back to full speed. If I reset the board by sending the code again, we're going to slow down again. But let me hit it with the flashlight for you so you can see what I was seeing. And you're going to see in real time here that that's going to move much faster once it hits 100%. It's going to take a little bit of time because of that 500 millisecond delay. But this is the perfect example to show you why you don't want to add delays to your code if you don't need them. Almost there. And once we hit it, we're going to fly. And there it goes. It's sped right off. And as advertised, if we go back to the bench, there's the LED. It's back on again. It's not blinking anymore. Just like what you saw the first time. Super speed, exactly. Because the delay that we have is only 100 milliseconds between cycles in this code, right? Now, I'm not going to lie to you. I kind of don't know what happens if we don't have that delay in there at all. I would technically still need the delay to see the LED blink, but I mean, we could find out. If we don't worry about blinking the LED and we don't delay it. Let's see how fast it charges. Beep, 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 bing, and it's done. I can hear the transmission shifting with that one. Oh, my ears were in the way. Hang on, let me do that again. Let me do that again. You want to see super speed? This is super speed. Dump the clutch. Let's go. Now it's going so fast that the serial terminal is actually having trouble printing this to the screen, which is why there's a little bit of a delay there at the bottom. Now if I take a look at the bench just to see, takes about, oh, that's right, I had that code turned off. Oh no, I don't have that code turned off. It takes about 7 seconds, I think, about for that LED to come on. Because we dumped the clutch. We went real fast. I'm probably gonna have to see a mechanic. We probably burned out some parts. No, this doesn't damage anything. I'm making funny car references because I can. But it goes to show you that the lack of the delay there is literally a case of gotta go fast. We are literally pulling those vibes from the little blue Hedgie, which is different than the Asset Hedgie that does the amazing art that's here in chat. Yes, I will fill that in as a compliment. You are welcome. Ha! Got him. I wouldn't have it any other way. So yeah, I could do that. Hey, wait, no, you can't turn this around on me. You can't do that. Oh God, no. Asset, if you're making more of these for me other than what we talked about, I am sending you money. I'm paying you for this art, okay? We're not doing this. we're gonna come to an agreement. That's what's going to happen, okay? Yeah, I am more than happy to have you as my artist on retainer, but we need to talk. You, okay? You are artists. You make art, okay? No overload, Hedgie. We don't do that here. Yes! Your boss is gonna burn you, and there's a good chance this toaster is gonna end up on fire. All right? That fireball is gonna be big enough that we're both gonna be in trouble, okay? Don't do that. We both would like to live longer. And if by some chance your boss is watching, love you. Hello. I hope you're feeling better. Drink more soup. Yeah, that's the emote of the screaming toaster, but yeah, no. Close enough. Oh. Okay. Wob. I have melted my brains. Das ist gut. Ba-ba-da-ba-ba-ba-ba. Alright. I'm gonna take us all over to Blake the Protogen, because he's another toaster. And then I'm gonna get us a raid message together here real quick. That didn't put that where I wanted it to. Come on. Oh, I gotta be fast. All right, folks, that is going to be the raid message. we will continue doing more silly things come next Wednesday. Thank you very much for stopping on in. I had a lot of fun, and I hope you have too. So, with that, we are going to have some fun popping over to say hello to Blake. So, be safe, drink some water, go chill out, and enjoy the rest of your night or day. Bye-bye.